It's good practice, and this is something that we need to practice, although we'll practice it in chapter 4 too. So 42 was looking for the resultant. Is that right? I don't have my book with me, so you guys got to help me. Yeah. Yep, resultant and distance. Did they care where from? From A? From A. So in the future, like quizzes and exam type of thing, you're going to get to choose where you do this from. So they're telling you, but really you can choose. And there are easier spots and there are harder spots. So we'll talk about that after we get through a few. This one had a couple forces at an angle. And I've already done it to kind of move through it a little quicker, but stop me if you don't, like, if I'm doing something you don't get, like, what's he doing? You got to stop me. So this one was, the angle was given at 75. This one was given at 12.5 rise run thing. So that's immediately I turn it into an angle. And I don't know why, but I did this upper angle this time. So I used this tangent 5/12, 5/12. So that gives me this upper angle. Once you have the angles, then next step is just turn them into their components. Like get rid of those angled forces. Okay. So that means I turn the 15 into its two components and keep their direction correct. In other words, 15 has down effect and it has to the right effect. Those two effects. So hopefully we know how to get those by now. Opposite the angle is going to be sine, and that's going to give me the y vector. Okay. Cosine is adjacent to the angle. That's going to give me the x vector. So I didn't write that out. I just did it, right? I went sine 75 times 15 is that one. Cosine 75 times 15 is that one. Okay. So then I did this one. This one has down effect and it has to the left effect. So that's these two vectors. Same kind of thing. Once you figure out the angle, the x this time was opposite the angle. So that's sine 22 times 25 for that thing. And then cosine 22 times 25 for that thing. So write them out if you need to. Just don't get them twisted. Like if you get them flipped, that's not good. You know you have it right, especially with steep angles. So this is a pretty steep angle, right? Like it's near vertical. So the vertical effect is going to be a lot larger than the x effect. That's how you can kind of double check yourself. This is pretty steep also, 75, right? So that vertical effect needs to be bigger than that translation in the x effect. So you can double check yourself just by looking at the vector going, oh, that's a lot of down. That should be big. That should be small. That's a lot of down. That should be big. That should be small. When are they the same? When it's at 45, right? If you have a vector at 45, then x and y are exactly the same. All right. Once you get it into components, then you collect everything. So then I'm like, okay, everything moves over here and I collect. I literally sum the moments and I sum the forces in both the x and y. So forces in the y, that's the 10, the 14, and the 23, and they're all going down, so they add up. That's all that is, just adding that, that, and that. And then same with the x. There's two of them, they oppose each other. So we got 9 here, 3 here, should be like close to 6, right? Yeah. So then I just add up the x's. Everything just gets moved over to A. The x effects go right through A, so they produce no moment. So the only moment you have is that times its distance, that times its distance, and that times its distance. So I actually wrote that out, 10 times 8, and they're all this clockwise negative moment. 10 times 8, 14 times 14 And that's the 8 and the 6. And then the 23 times 19, 8, 6, and 5. So they're all negative. So they add up to a negative 721, 306. So we've collected everything here now. Moment, down force, left or right force. Once you have that, these two are the components of the resultant. These two are the components of the resultant. The book will refer to this as our Y and this as our X. It's fine. You know, whatever. So then we just Pythagorean theorem out the R, because we have the two rectangular components of the resultant. 4791. Doesn't tell me the angle. I still need the angle because I know it works at an angle because we do have an X and a Y. It's kind of steep. This is small, 5.7. This is large, 47. So it's going to be pretty steep, and it was 83.13. So I just use tangent, right? Because I have this coming down and then this going over, and then R closes it. So I did the tangent of the Y over the X to give me this angle to horizontal. And then you need to know where it's at. So this is a tricky part that we did right at the end of the last class. We know we're going to divide the moment by a force. So you want to take that moment, and divide it by the Y force, because the X force does not contribute to the moment, it goes right along the X axis. So you just take the 721 divided by the Y force, the Y component, to get that X distance. So 721.47 gave me 15.16, and that's where R goes. What you put in is not the Y component, but you put R in, the resultant. Long problem. Long problem, lots of opportunity to kind of make a mistake. So you just got to go super carefully through it. Questions? Questions? Any questions? Clear as mud, clear as sunshine, clear as a blizzard. I don't know. You tell me. Early in the morning. This is non-concurrent. Find the resultant. Single force that replaces 1, 2, 3 forces. All right, I'm going to keep going. 44 looked like this. And I think, again, didn't have my book, but they must ask for where the resultant intersects the ground or something. Is that what they wanted to know? Find the resultant and where it intersects the ground. Is that true? Yeah. So find the resultant means move everything to one spot. This is a non-concurrent. All these forces do not intersect each other at one spot. So that means we have to collect everything at A. They took my triangle. Makes me angry. So what are all the forces in the X direction? How many are in the X? One. Which one? Yep, the 200. So I move it down. What do I got to do when I move this down here? I have to find the moment. What is the moment? Yep, 200 times 1.33, right? 266 And its rotation is, yeah, it's going that way, clockwise. So 266 Newton meter. So the 200's moved. How many forces do I have in the Y direction? How many of them? 2 of them. The 80 and the 50, which adds up to 130. Right? Because they're both coming down 130 newtons. And I got to move those. So what's the moment of the 80 about point A? Moment is force times distance. Yeah, it's 80 times 1, right? So if I moved it down and the perpendicular distance is right here, 80 times 1. And its rotation is the other direction. It's rotating that way. 80 Newton meters. And then what's the 50? Bring it down kind of close. Perpendicular distance is here at 2 meters. 50 times 2 is 100. Rotating that way also, counterclockwise. Yeah, so I moved the 50 by going 50 times 2. And the 80 by going 80 times 1. So that puts them all down here. The 266 is going the other direction from the 100 and the 80. So when you sum your moments, you're going to have 180 going one direction and 266 going the other way. Right? That was my foot. Oh, that worked. Kind of funny. 266 enter. 180 minus, looks like 86, right? 86 left over this way. 86 Newton meters. Here's my point A. So there's the sum of my moments. And the sum of my vectors I already had at 200 and 130. Right? And what they want to know is where is the resultant? Where is it on this horizontal line? And how big is it, right? So this is the X effect. This is a Y effect of the resultant. To get the resultant, I just do Pythagorean theorem, and it's going to be, looks like it's a little more in the X than it is in the Y. So it's not as steep as the other problems. Well, that was a couple questions. The 200 and the 130. 86 is the Newton meters. That's here.
What's the main role of that?
That's the moment, isn't it? Did I do that wrong? Summing the moments equals what? The 130 is the Y effect. Yeah, there's 2 in the Y, 50 and 80. That makes 130. Because I just add them up. They're both in the Y, they're both going down, they add. Okay.
You did 50 times 2.
That was for the moment. Ooh, different thing. That's a moment. Remember, moments are force times distance. But this is not a moment. This is 80 plus 50 newtons. This is just adding 2 forces together. right? 80 and 50. Just like the 200 was all by itself in the X direction. That's why it's here by itself. The 86 is that thing, the rotation, the moment. The units give you the clue, right? This is just newtons. Almost wrote pounds. Right? And this is just newtons. This is adding two forces. That's a newton. That's a newton. Those are just forces. That's a moment. Newton meter. Good? Dan, are you good? Okay. So then how do we get R? Pythagorean theorem between what two numbers? The X and the Y force, which is the 200 and the 130. 200 squared, 130 squared, add them together, take the square root, 238.54. Newtons, because that is the resultant, right? And why did I put it down and to the right? What tells me that the resultant goes down? Has down effect. Yeah, that's telling me it has down effect. What tells me that the resultant goes to the right? The 200. Yeah, exactly. That's how I know it goes down and to the right. I should calculate that angle, theta, so I know exactly how much down and to the right. Well, that's going to be the down effect, the 130 and the 200, and I just do inverse tangent of 130 over 200. .02 degrees. A lot of times we want it to horizontal. That's very common. Now, where's it at out here? This X distance. Because it's out here somewhere, right? It's not at A. If we look back at this problem, they wanted to know, like, where is it out here? So how do we determine where this is? We're going to divide the moment by a force. What's the moment? Yep. And which force do we want to use? Yeah, for sure matters. Big time. Yep. We have three forces to choose from: 200, 130, or the resultant. If we do the resultant, the perpendicular distance is to the resultant, which would be some weird perpendicular distance. We don't want that. We want this distance along here. So what force is perpendicular to this horizontal line? Yeah, the Y force. So if you divide by the Y force, you get a X distance. And that's what we want, is this nice, not that X, we want this X distance. Nice X distance. So we divide by the Y force, 130 newtons. That's the Y force. So much glare, I can't see what I got here. 130 divide. I get 0.66 meters. That's where R is. We're getting there. Like, you know, everything gets weird when we do a vertical problem because these are all horizontal problems. But once we think it through, if we want a vertical distance, we would divide by an X force. If we want a horizontal distance, we divide by a Y force. Right? So there we go. Yeah, it requires a lot of repetition. I've had the luxury of like 31 years of repetition plus when I was in college, so plus when I was engineering, so it's super easy for me, but you gotta slow me down if I'm going too fast. All right, 65. I did not have a picture of. What's 65 look like? I got 67, I think. So like a cantilever beam? Oh, nice. Okay, hang on. This is good for me. I gotta follow verbal instructions. So I'm gonna call that A. What's 5 feet? 3K vertical? Okay. Is that like in the middle? Okay. Oh, good. 5 feet and 5 feet. $3K or $5K? Anyone want to break the tie? That's helpful. Number 65, chapter 3. $5K there and then 5 at the end. 5 feet on both sides. At the end. I'm confused. You gotta help me out here. No, don't show me, tell me. Well, I wanna know. It's not 5K. Okay, 3K. And then what's at the end? Okay, perfect. Love it. That's okay. So it's still that angle? Oh, 4-3. Yeah. So like this. And how much force? 4 down. 3. That's rise of 4, run of 3. And then how much is the load? 5 kips. Yeah, that's it. And this thing's like a cantilever. Yeah. So cantilevers, we always want to know what's going on at the support. So that's probably point A, right? Yeah. And they want to know the resultant. Oh, just the moment? Oh. It's kind of a piece of cake. Not completely piece of cake. What do I do first when I see forces at an angle? Get the X and Y of it. Turn it into its components. I know there's down effect and I know there is to the right effect. Yeah. So I would find the angle 4-3. So I'd go 3/4 and inverse tangent to give me that upper angle 36.869. That's this thing. If you do the other angle, it's fine. You just got to keep track of which one you're doing, right? So then I know opposite of that angle is going to be this X force. So I'll take that 36.869 and do the sine of it and then multiply by 5K. 3.
I did cosine instead.
That's fine. That should work. So cosine is just going to give you this, but we've done this triangle once before. It is a 3-4-5 triangle. So the X is 3, the Y is actually 4K, and the hypotenuse is 5K. It's a 3-4-5 triangle. So there's very few triangles that have these clean ratios to them, but this is one of them. I just know a 3-4-5 triangle. 3-4-5. If the legs are 3 and 4, the hypotenuse is 5. So they gave you the ratio 4-3. When you see that And if you remember, hey, this is a 3, 4, 5 triangle. So that's kind of handy. Once you put in the components, the 5K is gone. And the effect is exactly the same. Since I did it in pencil for this problem, to emphasize it, I'm erasing it. So that is exactly the same as having the 5K in there. That was Varignon theorem. It's just a party trivia thing you can remember. It's important stuff. All right, now we have it into its components. They want to know the moment, right? So what's the moment of the 3K about point A? Yeah, 3 times 5, right? 15, which way does it go? Yep, 15 kip feet. So now the 3 is moved. Its rotational effect is moved. What is the moment of the 3K about point A? 0, no distance. So it does not contribute to the moment. What about the 4K? Yeah, 4 times, yep, 40 kip feet. Excellent. What is the sum of the moment at A? 55 kip feet. And it is rotating clockwise or negative.
What I did was 5 cosine and the angle 36.86.
Yep.
7 times 10. Does
Yep.
it make a difference?
No, you're just not breaking it down into the pieces. That's fine. As long as you're writing that out, I can see that.
Find out in like future references that it's like a 3, 4, 5 times.
Just memory. I mean, you'll calculate it and it'll come up. One leg will be 4 kips, like I did. From the 4 ratio, 4 kips, and from the 3 ratio, 3 kips, and then you'll go, oh crap, that was a 3, 4, 5 triangle. Yeah, I just remember it. Is that all they wanted? Was a moment? Yep. There you go. This is the important thing when we get to strength of materials. Knowing the moment at point A, we can then calculate the bending stress of the beam and determine if the beam is safe or not just from that number. We always are going to check it in shear stress too. So that's what these other 2 numbers would be valuable for, especially this down force of 7. So anyway, good. Excellent. Moving on, 67. That's this one. Make sure I copied that one down right. 300. Yeah. Yeah, triangle. Yep. Nope. Careful with your units. 60 pounds per foot. It's not a torque. It's not a rotation, right? It's a load. 60 pounds every foot. Every foot, 60 pounds. 300 pounds per foot is the ratio going to 0. Yeah, every foot is 60 pounds. It's a distributed load. So that means like it's a stack of plywood, or it's a bunch of bags of concrete, or who knows what. Drift of snow over here, right? It's distributed, not concentrated. All right, so how, and they want the resultant, I'm guessing. Yeah, magnitude and location of resultant. So what do we do first when we see distributed loads? Get rid of them. Concentrate them. So how do we concentrate a distributed load? We calculate the area of the load.
So I think area of a triangle was it 1.5 times 300?
It's 1/2 base times height. Yep.
Yeah.
Yeah. So that's the area of a triangle. So 1/2, the base I have at 6 foot. You can do this in any order because it's multiplication. And then the height at 300 pounds per foot. Right? So I can do that math in my head, maybe. We got 1/2 of 6 is 3. And 3 times 3 is 9. Yep, 900. And what's the units? Yeah, because the feet cross, right? And we're left with pounds. That's our concentrated load for the triangle. Where do we put it? Through the geometric center of the shape. The shape's a triangle. If you don't know the geometric center of a triangle, you look in the front cover of your book and it's going to tell you that. It's 1/3 from the 90. So here's the 90 degrees, or 2/3 from the pointy end. Yep, which is 2. So it's right there at 2 feet, and it is 900 pounds. And that's exactly how I do it. I usually leave the triangle there, but I'm only going to use the 900 now, right? I just concentrated that distribution. Excellent. And then the rectangle, that's an easy one. Length times height, 10 times 60, 600. And where's it go? Wait.
Isn't it 60 times 20? Oh, no, 60 divided by 20.
Yeah, so just the distribution.
50 divided by 20 times.
No, not divided by. What is the area of this, Ben? Right here, this thing, this distribution. The height is 60. What's the base? 10. 60 times 10. 600. Just like you did this one, you did this area. Area of the triangle. Now we do the area of the rectangle. Where does it get applied? 5 feet on each side, right? 4 feet is here. Once you have them concentrated, you're ready to go to work. And we know we have to just collect everything at A. What are all the down forces? What's our downs? 1,500? Yeah. Sorry, I heard you say 500. I'm like, what? 1,500 pounds down. That's the 900 and the 600. What are all our X forces? There are none. No X forces. So just have that. And now I need the moments. 900 times 2. 1,800 pounds, and 600 times what? Be careful with this. I have a lot of numbers there, trying to mess you up. Yeah, it's going to be 600 times this 4, that 5, and that 6.
So you did 2.
Yep.
plus-
That's correct. And my calculator went off. 9,000. Right? So we just add those together. So now I know the sum of the moments is equal to what? 10/8. 9,000 plus 1,800. Yeah. So, trick question, what's the magnitude of my resultant? What does R equal? Not too tricky. Yeah, 1,500. 1,500 pounds. That is the magnitude of the vector, the resultant. Now, what do I use this moment for? Right? But also, doesn't it tell me where 1,500 is? Yeah. So I know 1,500 is out here somewhere, but where is it? It's at some X dimension. Right? So that's where we take the moment and divide by a force to get the distance in the X. So moment is 10,800. Force is 1,500. $7.2. Distance to the resultant. Whew. Good times. Questions? What do you think? Did you do it? We have an exam in a few days, week. It's not this week, it's next week. And this is the kind of stuff you get to do. Yeah, parallel system is less complicated, that's for sure. Like, once you get the 900 and the 600, you just add them up to the 1,500. So, and then once you have that and your moment, you just divide it out and that's where you put it. So it's not too bad, not as complicated as the ones with the angled forces. Like that first one, you know, that's more kind of just more steps to it. Once you get it here, then it is just, you know, horizontal, vertical stuff. So good to have that process down, written down so you can refer to it. It's open notes, the exam's open notes, and actually it's open homework problems too. If you have that, you can have all that in front of you. But I'm not going to give you a problem exactly like a homework problem. You'll have to think it through a little bit. So try to resist like, oh, here's a homework problem that looks just like this problem, and then just copying it over without even thinking about it. That's not a good way to go about it. So I think you guys are getting it. So we have a few more days. 73, right, Ben? Yeah, that was another one with an angled force, correct? Yeah, so this was a little tricky. I didn't notice it, so, but I noticed it right off when I wrote the problem down that they mixed units on you. So we really hadn't talked about that. Sorry about that. But you can't do a problem with mixed units. You have to get it all into the same unit, right? They didn't mix metric and US. That'd be really rude. I would not do that to you either. So, but you got to watch for it. That's for sure. So this needs to go to maybe all, I don't know. I'd probably go to kilonewtons just to keep the numbers small. But you can't have three different ones: newtons, kilonewtons, and meganewtons. So what's mega? Anyone know what mega means? 10 to the 6 is mega. It's like a million. And that's 6 zeros. So when you win that lottery, that's a lot of zeros. So mega means 10 to the 6 newtons. you know, if we went to newtons, that would be 0.12 and times 10 to the 6. That would be 120,000 newtons. So we could do that. Numbers will get big. And then what's kilo mean? That's 1,000, yeah. So that's 8,000 newtons. So if we go 120,000 newtons, 980 newtons, and 8,000 newtons, then we're all in the same unit. We're all newtons, right? If I went to kilonewtons, this would be 8 kilonewtons. This, you just move the decimal 3 places to get kilo. So that'd be 0.98 kilonewtons. And then this 12, you'd move it 3 to the right and you'd get 120 kilonewtons. So again, however you want to go about getting them all to the same unit, that would be step 1. If you didn't do that, then you ended up with a mixed unit problem, which is definitely a problematic for sure. All right. So we got it all to the same unit. Now what? What should we do next?
So for the 8,000 newton,
Yep.
gotta equal 40 degrees to the top.
Yep.
I was thinking sine of 40. So that I'm like, okay, we can't divide Fy by 8. How is that?
So I think what you're saying is turn it into its components. Yeah, that's exactly right.
50 degrees.
You can use either one. Just build your triangle. Yeah, it doesn't matter. So I'd use the 40. It's right here. So then I'd build my triangle here and here, right? So then sine would be the y and cosine would be the adjacent. If you use the 50, it's just going to switch. Okay, because the 50 is up here. So then sine of the 50 would be the x and cosine would be the y. But you can use either one, just kind of keep track of it. I'm going to use the 40. So sine 40 times 8 is going to be the y.
Oh,
Here,
okay.
I'll draw it. So if you are getting confused, draw the triangle. Yeah, exactly. I do that. It's like for real. I do that too. So this is 8,000 newtons. This is my y. This is my x, and this is my 40. Right? So you just kind of pull it off and draw the triangle and use either the 40 or the 50, doesn't matter. So then I know, okay, opposite my 40 is going to be the y. So that's going to be sine 40 times 8,000 is Fy. So then that means Fx is cosine 40 times 8,000. So just pull that vector off to the side, build the triangle, and make sure you get it right. It's worth the extra time just to draw the picture. So y is 5,142. .3001. And then the x, 40 cosine, is 6128. .3, lots of 5s. Just gonna round it there at the 3rd spot. Make your drawings big, and this isn't, I mean, I could have made it bigger, but it just gets really busy. Or make multiple drawings, you know, make another drawing where this is gone and you just have the X and Y in. However you want to keep track of it. Next step, what's our next step?
Oh, find what was the result? Or was the moment? What's the moment? Because we gotta find something about the point A.
Yeah, those two steps, it doesn't matter what order you do them in. Oh, boy. All right. No resultants, just 2 moments? All right. Yeah. Okay, so let's do the moment at A. So I'm gonna write it out in long form. And I'm gonna use good notation, summation moment at A. So if that's not on your paper, it's gotta be there, or else I don't know where you're doing your moment, right? So you gotta somehow tag where you're doing your moment in the equation. And I'm just gonna write it all out. So moments at A, I have 120,000 times what? Yep. And positive or negative rotation? Negative. Clockwise. Everyone good with that one? Doing moments at A. Remember where you're doing it. 980 times 6 meters. Rotation negative clockwise. And then what creates moment? The Y or the X? The Y creates the moment. The X does not, it goes right through the point. 5142.3001 newtons times its distance. 13? Negative. Right, 7 and 5 is 12, plus 1 is 13. What'd you get? Anyone get a number? If you didn't have crossed units. Our numbers are getting big, aren't they? One 192,729. 192,729.901 Newton meters. Rotating clockwise. Good. And then summing moment at B. So no reason to do this other than practice. So the book's just making you like grind out some practice. So moments at B, X drops out. I have the 5142.3001 times, is it 3 meters? And that rotation is going to be positive counterclockwise. And then we got the 980 times 10 meters. Same thing, positive. And then we got the 120,123, 120,000 times 15 plus. Yeah. Oh, there we go. Oh, shoot. Screwed up. Too fast. One, 8, 2, 5, 2, 6, 6. Anyone else get that? 1, 8, 2, 5, 2, 6, 6.9 Newton meters, and that is going to be spinning the opposite direction. So moments of both sides. Not too difficult. And then they wanted the resultant. Yeah. What's the resultant? How big? What's the magnitude of the resultant? You can just tell me, even if you don't know the number, how would you get it? Add what together? The Y forces. So 120,000 plus 980 plus 51423001 to get everything going down, right? And then in the X, it's 6128,356. Once you get all the Y down and all the X across, you do Pythagorean theorem to get the result, right? So you got to add up all the Y's. Got to add up all the Y's. Do it. You do it, I'll do it. Your phone, it's not going to work, man. 120 down, 980 down, 5142. See if my red pen works. Down I get 126. Yep. Yep. And then what do we have in the X? What do we have in the X?
Oh, yeah.
Yeah, there's only one, right? There's only one little force in the X. It's not little, it's 6 grand, but it's not anywhere near the 126,000. So the resultant's pretty vertical, but it's not totally vertical, right? And how do we get it? Pythagorean theorem, over and over and over. There's R, it's green. So got to square them both. Add them together and then take the square root. Correct. If there's no X, you don't have to do Pythagorean theorem, right? You just have these Y forces, add them up, you're done. That's why that parallel system is a lot easier. There's the resultant. I get 126,271, right? That resultant, I mean, that's all there is. Doesn't matter where you did your moments, because the moments is just a different thing, right? The resultant is just the forces, combination of all the forces. So find the resultant, that's it. 126,271. It's good to know, good to know what this angle is, theta. Right? We always want to know the angle that it acts on. So that'd be the inverse tangent of Y over X. So 126, 122.3001. We have big numbers. Gonna be close to 90, 87.22. 87.22 degrees. And the last thing we'd want to know is where is it at? Like, where is it on this beam?
How'd you get there at 87 hours?
That angle?
Yeah.
So it's this angle here. So if I did inverse tangent, what would I do? Opposite over adjacent. So it's y over x. 126,122.3001 divided by 6128.356 inverse tangent. Because to fully define a vector, you got to have magnitude, direction, that's the angle. Sense, which is the arrowhead pointing down, right? And then point of application, like where is it on this beam? So those four things. That is on the exam. So the exam's going to go all the way back to like chapter 1. Like you could have a trigonometry question on the exam, right? But I could ask you things like, what are the four characteristics of a vector? I probably wouldn't ask you that because you can just look it up in the damn book, right? But I might ask you something else about the characteristics of a vector. So yeah, we'll do a review on Monday. You take it on Wednesday next week. Okay. Where is it on the beam? How do I find out, like, hey, where is this thing out here on this beam? Like, I know it's out here somewhere. Moment divided by what? Which force? Yes, the y force, because we want an x direction. When you have two forces, you do an x and a y, divide it by the y, you'll get an x direction. All right. What was my result at 126, 271? Oh, I got that number. I don't have to input that thing. And I need the moment. Which one do you want to use? We did two of them. Does it matter? If I use the moment at A, where's my distance come from? A, exactly. If I use the moment at B, where's my distance come from? Moment at B. Doesn't matter which one you use. You just got to know which one you're using. That tells you which way you're coming from. I'll use A, right? And then I'll know I'm coming from point A. Moment at A is 192. 729. 901. Oh. Goofed up. It's all right. $1.53. From A, because I used moment A. That's what I got. I got 1.53. It's a lot. We're now taking a break. Break time, break, stand up, turn circles, whatever you got to do. All right, what do we do first? We want the resultant. Well, that point A. Non-concurrent, we want the resultant. What's got to happen first? Step one. Yeah, concentrate the distribution. Step one. Get rid of the distribution. If you see one, if you don't see one, then you obviously don't have to do that. But if you see a distribution, get rid of it, concentrate it. So I know it goes here. And I know it's the area of the triangle. So that's the 8, 1/2 base times height, 1/2 of, I'll do 1/2 of that because it's easy. That's 4 times 9, 36, right? 36 kips. And where's that at? Through the geometric center, which is 1/3 the base from the 90 degrees. So that's going to be 3 feet. Once you have it concentrated, if you want to know the resultant, you move everything to one spot. Where do you want to move it? Sure, why not? We seem to be a very left to right country. Point A. So all the vertical forces, add them up. 36 plus 5, 41K. Are there any X forces? No. That's a good thing, right? Simplifies the problem. When we move forces, what else do we have to do? I'm looking for, I think you're in the right path, but I'm looking for the right terminology. The 41K collects the up and down effect. Yeah, we need the rotational effect. So we have to bring the moments with those vectors. We moved the 36 over here. I need the moment, which is what? 36 times 3, 108. 108 kip feet. We moved the 5K over here, so I need to bring the moment with it. That's going to be what? 5 times 13, correct. 65 kip feet. Right? When you move a force, you take its translational effect. That was the 41, and we added 36 plus 5. And we bring the rotational effect. So our total moment is, these are additive. 108 plus 65. Total moment is 173 kip feet. Right? That's the sum of the moment at A. How much is the resultant? What's the magnitude of the resultant? R equals, 41K. And then now we just need to know where it's at, because here's my beam. R is out here somewhere, 4K. We just need this X distance. Take the moment, divide it by the 41. 173 enter 41. Divide 4.22. Done. When you don't have an X force, it's pretty simple. Just that Y force, add them up. Piece of cake. Piece of cake, piece of cake. There'll be one like that on the exam, nice and simple and straightforward. So don't make it more complicated than it is, because we've done complicated ones and simple ones. So, all right, let's talk about chapter 4, because it's a bit of a game changer. So we kind of got to go backwards a little to remember what a concurrent force system was like. So concurrent force system had something like, there's a force, 100 pounds, and there was another force, maybe that was like 50 pounds. And I'll put an angle of, looks pretty steep, 80 degrees. Right? So that was a concurrent force system where the forces all come from one spot. That's like chapter, I don't know, 3 maybe. Right? Chapter 4, no, chapter 2. Something like that. Chapter 3 was non-concurrent. And what we did was we found the resultants here. Right? We said, oh, those two add up to some vector. Right? Huh? Yeah, okay. So now in chapter 4, we want our systems in equilibrium. So equilibrium means that the sum of the forces in the X is equal to 0. Okay. And the sum of the forces in the Y are equal to 0. Meaning that all of these effects in the left and right add up to 0. That's what's going on in the building right now that we're in. All of the forces in the Y equals 0. The building's not going into the ground. It's sitting here. And the wind's blowing on it, but it's able to resist the wind. All the forces in the X are equal to 0. That is equilibrium. Okay. And all of the moments must be equal to 0. All the rotational effects have to be equal to 0.
What if it's like 1?
Then something just fell over. It's true. If all the forces in the Y were not equal to 0, like if we had some extra force in the Y, like it snows a whole bunch, and that just pushes the building into the dirt, just pushes it right into the ground, then all your forces are not equal to 0. So that's when things go bad, when we're not static. Right? So that's when things go bad. That's when things break. If this desk right here, all the forces are equal to 0 on that desk, right? If I take a truck and set it on the desk, what happens? It like collapses it. All the forces in the Y were not equal to 0. If it holds it, then woo, that's cool. All the forces are equal to 0. Yeah.
Well, we calculated the resultant moment on like a piece of paper is one thing.
Yep.
If you're comparing it to an actual building, and from scratch, you're trying to calculate how much.
Yep.
Count on each side.
Yep.
How much is that?
You very carefully. Like
How?
time consuming, like you just like figure it all out. Like when I was designing the trucks, all the components they want to put on the truck, I had to like account for every component, every nut, every bolt. They're paying me good money to do it. I do it nice and slow and I figure it out. That's the job though. That's it. That's what you do. Right? Yeah, it's time consuming. Big jobs are time consuming. Buildings are big jobs, right? So here's my camera. If I push on it with a little bit of weight, it doesn't tip over. So the camera is resisting, the base is big enough, heavy enough, that it's resisting that rotational effect, right? It's static. I push on it. If I push on it a lot, it starts to go. Now the sum of the rotation is not equal to 0. Okay? That's what we're talking about, statics. Everything has got to be static, not moving. These, all three have to be true. So is this in equilibrium? No. We definitely have forces in the X and forces in the Y. I want to make it in equilibrium. I want to say, okay, I need to add a vector that has down effect, because this down effect will fight that up effect, right? And it must have left effect to fight the right effect. This now is going to be what I call just, I'm not even going to call it R, I'm going to call it F, right? F is going to put my system in equilibrium. So in chapter 4, we say, okay, there is no resultant. We can't have it. Can't have it at all. So how can I determine what force I put in there? So we have to figure out the angle, but we have to figure out the Y effect and the X effect to make this true. So let's look at the easy one, the Y effect. Why is the Y effect the easy one? Because this is all in the X, it doesn't contribute to the Y, correct? This is Fy of the 50, right? This is the Y effect of that. This has Y effect, Fy of the F. How much does this have to be equal to? If there's only two, and they've got to be equal to 0, they got to add up to 0. This one has to be equal to that one. That makes sense? So can I find this one? Absolutely. I know 80 degrees. I know the 50 pounds. I can get that. How should I do it? This is opposite the 80. Careful. Sine 80 times 50. What is that? $49.2404. Everyone see how I got that? That's just a component of this critter, right? Yeah. And that is equal to that. It's got to be. These two have to be equal in order for this to be true. Make sense? Same thing in the X. I have X effect from the 50, and what other X force? The 100 is all in the X, correct? And then, yeah, this Fx of F. In order for this to be equal to 0, that plus that plus that have to be equal to 0. So essentially what we do is we sum forces in a direction, sum forces in the X, because I'm doing X's now. So that's going to be plus 100, right? And then this one, which is going to be cosine 80 times 50, that's that, right? Same way I did this, but I'm now doing it for the adjacent. So that's cosine. And which way does it point? Negative. And then, which way does this point? Which way does this point? Negative. And I can write the equation. So it's adjacent to, or I can just write in Fx of F, right? Since that's what I named it, Fx of F. Usually they're going to say it's like F1, and then this would be F1, but right? That is the component of F that puts this all into equilibrium or equal to 0. So you build these equations and then solve for this thing. The whole thing's equal to 0, but no force is equal to 0. Yeah, the whole thing's equal to 0. So that means this can move over here, right? Become positive. And then it's just this, which that's a number and that's a number. 91.318. That's how much puts it in equilibrium in the X. That up there is how much it puts equilibrium in the Y. Now you have the two components of F that puts the whole system in equilibrium. That's chapter 4. Chapter 4 says, hey, there's no resultant. We can't have a resultant. We have to figure out like what is going on to put it in equilibrium. Okay. Once you have the two components of F, then you can get F. So F equals the square root of, right? This is Pythagorean theorem, 49.2404 squared plus 91.318 squared. $103. And yep, you'd need an angle to know it's down like that. You'd need to know that angle. So you'd have to do your trig to calculate it out. The three equations of equilibrium are this, and all three have to be true. Now, this is a concurrent system. There are no moments. So in concurrent systems, we don't have to think about moment. We just think about summing X and summing Y. Right? Your homework starts with these concurrent systems. So you kind of go back and like, oh, concurrent systems, everything's in one spot. To find out how to put it into equilibrium, you apply these two equations. All the X's got to be equal to 0. All the Y's got to be equal to 0. Yeah, you'd need to find the angle, but you all can do that now. You're pros. Right? If I wanted this angle to horizontal, what would it be? It would be Y divided by X inverse tangent. Right? So here's Y divided by X inverse tangent. I'll let you guys do that. You might have a free body diagram problem too, so I should talk about that just briefly. But you'll have these where you're like, oh, I got some forces in the X, some forces in the Y. And then I think they might introduce non-concurrent. So let me just give you a feel for that. You might need to do a little reading out of the chapter because it probably starts with something like this, where this is 6 feet, 10 feet, 5 feet, and 100K and 50K, right? So non-concurrent. And what they're going to have you do is, since we got to put this in equilibrium now in chapter 4, we have to say, oh, these three equations got to be true. Right? So we need some opposing forces for those down forces. And that's what these are, these supports. So I think it'll introduce you to these supports and what they do. So I'll just cover two of them, but they're in the beginning of chapter 4, I'm pretty sure. Huh? What? Yeah, there's a little table. So a roller is a circle, and it's allowing the system to move this direction. So these are called expansion joints, and this is just how we draw them. So like when this heats up, it needs to expand, or when it cools down, it's going to want to try and contract. We want it to do that. We would like bridges to expand and contract so we don't introduce thermal stresses. We do thermal stresses next term in strength of materials, but a roller is just supporting in one direction. It does not support in the X direction. So the first part of chapter 4 just has you draw these diagrams, like pull the roller out, put the support in, right? Well, for a roller, pull that out, I just put a vertical support in. Now, if the surface is at an angle and you have a roller, the roller supports perpendicular to the surface. So 90 degrees to the surface. Well, if this is horizontal, then yeah, we're just vertical. That's pretty common. And then this is either a pin, and we call them free pins, free to rotate, or what we call a knife edge. Either one, they do the same thing. They support up and they support in a direction, X to the right or X to the left. So pins get 2 reactions, rollers get 1 reaction. Okay. So the point is we're going to take these supports out and we're going to put forces in. Right. And these forces then will put these in equilibrium. When I sum forces in the Y, I have some opposing forces. So look at that, kind of look through the book a little bit. And if you have to draw a diagram, give it a try, and then we'll clean it up on Wednesday. There's a lot of stuff going on. Chapter 4 is big. You should do some reading in it. All right, we're done. That was way a lot. So nice job hanging in there.